we're going to kind of return to this idea of how we can rewrite the union. Okay? So let's say I have something like this, and we'll come back to it here in a second. The entire experimental outcome space is 1, right? That represents the probability of every single possible outcome. If I broke this down where I'm thinking about this white area here, well, that just represents the union of A and B. Right? If for now, I'm going to tell you that this is what it is, I'll show you why it is in a second, but everything that's not in this union of A and B, or this blue area, I can actually write that as the probability of the intersection of the complements of these two events. So the intersection of A and B complement. So if I took this blue area and I added to it the white area, that has to add up. It fills up the entire space. It adds up to 1. So this, right, if I add the probability of the union, that's the white area, to the blue area, or the intersection of the complements, these two things have to add up to 1. Okay? From there, I know that I can rewrite the probability of the union as the probability of the two events minus their intersection. So if I just substitute in what I already know for how I can rewrite that union, I know that this equation, these 4 components, have to also add up to 1. Okay? So anytime I don't know one of these, as long as I know 3 of them, I have 1 equation, 1 unknown, I can use algebra to solve for it. All right? So we'll work through a couple examples like this. But before we do that, I'll try to give you a little bit of insight as to why this shaded blue area is the intersection of these two events. So we'll go back to our dot cam here. So let's draw an experimental outcome space. All right, let me try to get this straight here. So let's say I had something like this, and I've got event A, and I've got event B, right? So I kind of think about the area within those circles is the union of the two. Well, remember, before we did a very similar thing. Let's say I wanted to look at B complement. So I draw my vertical lines, everything that's not in B, right? I then want to take A complement, everything that's not in A. So I take circle A and start drawing these red or these horizontal lines if we don't have colors here, right? So it might be a little bit hard to see, but notice the only areas in which the red and the blue shaded area, the lines intersect, is everything outside of the union. So if it's where A complement and B, sorry, I should write this here. The red area here, the horizontal lines was A complement. So everywhere where the blue and the red shaded areas intersect, well, that means that I'm in both A complement and B complement. Right? So that's why everything outside the union, I said, I could think about as the intersection of those two events' complements. Right? That's why that holds. Okay? We okay with this? So from here, I'm going to go through 2 examples where it's once we know that equation holds, it's really just going to be a matter of doing a little bit of algebra. So I'm gonna have to hit this here. See if I can get it on the first try. I might have hit it a little bit too late. It'd be really nice if we just automatically did this, but nope. All right, I hit it a little bit too late. Now we should get going. There we go. So let's say I give you 3 of these pieces. Let's say I had a problem like this, right? I tell you the probability of A, right? And when I'm telling you the probability of A, it's this entire circle, right? The whole circle represented A. I don't know the probability of B, but I know the probability of their intersections, right? The kind of area that's in both of those. I'm also giving you the probability of the intersection of the complements, or this light blue or kind of grayish area out here. Well, I know that those 4 components would fill up this entire experimental outcome space. I can use those 4 to figure out that the union plus the intersection of the complements add up to 1, plug in for the union, the equation I know that holds, and solve for this missing piece. So how do I do that, right? Well, here's that equation. We know that if I take the probability of the two events and subtract what I double counted, which is the intersection, and then add the intersection of the complements, this kind of light blue gray shaded area, they have to add up to 1. So what I could do here is just start plugging in my values. The probability of A is 0.5, the probability of intersections is 0.1, the intersection of the complements is 0.3, and then it's just, once I have those plugged in, a little bit of algebra to solve for what that missing component probability of B is, right? You could actually, if you wanted to, once you plug the values in, just rewrite probability of B as X, and it becomes like a algebra equation, basically. But that's all we're doing, right? So plug in your values into that equation that you know has to hold, and then rearrange to solve for the one part that you don't know. Okay? Now, I'm not going to go, line by line, step by step through the algebra. If you're having problems like plugging this in, how did I get from here to here? Feel free to reach out. I'm kind of expecting that, it's kind of some prerequisites. You should kind of understand the algebra or be able to reproduce the algebra here. But if you are having issues or difficulties, like reach out, let me know, and I can kind of walk through. I'm just not going to take class time to do it, okay? But during office hours or even a time we schedule to meet, we can kind of walk through that a little bit more line by line, okay? So if we do that, we end up with we end up with 0.3. Any questions on what I did here? I know if you're just looking at the slide, it may be a little bit less clear. I tried to kind of give you some verbal, like, we're just plugging in our values and then doing our algebra to rearrange for the one thing we don't know, okay? Now, the one place where you can kind of get tripped up a little bit is maybe a little bit more apparent here, which is, let's say I ask you for what's the intersection of these two. So maybe the intersection of the two events is what I don't know. So I know that the entire circle B, the probability of B is 0.3. The entire circle of A, the probability of A is 0.3. This gray area, or the intersection of the complements, is 0.5. And I ask you to find me what the intersection is. Okay? The reason why this can become a little bit more tricky is if I use that equation, I have to remember there's a negative sign in front of that intersection. So when I'm rearranging, I have to remember that that negative sign is there. Right? So what I'll show you here is if instead of plugging the numbers in first and then rearranging, if I rearrange this equation to solve for the one thing I don't know, I'd have to remember that, look, I'm adding this to the other side, and then I would subtract 1 from both sides. So it gets a little bit tricky. Most of the time, if you forget that negative sign, it's okay because you'll end up with an answer that's negative, and you can't have a negative probability. So you know that you made an algebra mistake somewhere. You forgot a negative sign, right? Because we're still looking for a probability. It has to be between 0 and 1. Okay? So we rearrange the equation first this time. I mean, we can do it either way. I'm just showing you 2 ways. So if I rearrange this equation to solve for the thing that I don't know, now I plug my values in. So the probability of A is 0.3, B is 0.3, intersections of the complement is 0.5. And then it's just a little bit, entering this into our calculator, and we get that intersection should have been 0.1. Okay. So I think once we have that equation, understand kind of why it holds, this is really just kind of an exercise to a degree in algebra. Right? We're solving for the piece of the equation that we don't know. Okay. And more often than not, this will probably be the intersection of the 2 events, but it could be one of the other 3 components. Okay. Any questions on this before we keep moving?
Well, I have a question.
Yep.
So if I know that it has to equal 0.1 and I add up everything that's given and it's like or it's like 1.3, then can't I like automatically know that like what's missing is 0.3? Like if it's the intersection?
Yeah, you're for sure, right? You could do it that way. If you are looking for the intersection, right, and you add them up, they're going to be over the value of 1. So what you're saying is if I add these up and I don't include the intersection and I get 1.3, I automatically know the intersection has to be 0.3, right? I automatically know that in order for them to add up to 1, I'd have to be subtracting out however far above 1 I am. That's another way you can do that. That's a fine way of thinking about it. Yeah, that's fine. You're really just leaving off this component and knowing that you have to subtract it out. But yeah, that's perfectly fine.
Thank you.
The other thing that people get tripped up on is the way that this is displayed here. Don't think that like the probability of B here, don't think about it. Sometimes people can make the mistake of visually thinking about it as though it's this half moon. I really could have had it like here, right? It represents this entire circle. So that's the other common mistake I see people make that want to do this in their head, because you can very easily do this in your head without ever looking at the formula. But the problem most people run into if they do it in their head is like the visual. When you're thinking through this, I do the same thing. For some reason, you think about this probability of B as being like this crescent moon. And if you try to do it in your head, a lot of times people will kind of, I don't know, kind of get that wrong. It doesn't represent just this crescent moon. It represents the entire probability of B. Okay? Any questions on that? No? Yeah. Stretching. All right. Okay. So if we don't have any other questions up to this point, and I'll go back here and we'll kind of return to this. So any questions at this point? Okay. So I'm going to actually work in reverse. I decided that I like explaining things a different way first, and then we'll kind of come back to this slide. So one thing that I brought up on Friday, but we really didn't dive deep into it, so I wanted to save it for today, is this idea of conditional probabilities. Okay? So if I'm thinking about conditional probabilities, the way that we read this is the conditional probability of A. Okay? And the reason why we say it's sorry, I said that backwards because I was looking at the other one. This is the conditional probability of B. And the reason why we say that is because we're conditioning on something else. Whatever's on the right-hand side of this line, that's what we say we're conditioning on. So we're conditioning on A, but we're still looking for the probability of B. And the way that we usually read this is the probability of B given, this vertical line we kind of read as given event A has occurred. Okay? So how could this conditional probability change things for us? So I'll try to give an example that I like. I don't know if everyone else likes it, but I think it makes sense. And this is using a generality, but if we look at the data, this is supported. So let's say event B, right? So we're thinking here, event B is whether or not, if I ask a person at random, they are in favor of supporting marijuana legalization. So I've looked at the data for Indiana. I think it's like one of the last polls they took was like around 60%. So the probability if I chose one person at random that they'd be in favor of supporting legalization of marijuana is about 0.6, right? 60%. But now let's say, well, what's the probability they'd be in support of legalization given, so you have another piece of information, given that you know that person is a registered Democrat. What do you think probably happens to the probability that they're supporting it? I see people pointing out, right? It's probably higher than 0.6, right? I don't know the exact data on that one because I didn't have it broken down in the poll, but based off all the things that we've seen, voting records, we know that it's likely higher, right? And then if I told you what's the probability they support it, given that they're a registered Republican, well, you know it's probably going to be a little bit lower, right? Having this additional piece of information allows you to get a better idea about what that probability is. And that just makes sense. If I have more information about the person, I'm going to be able to not just use the average of everybody, but the average of whatever their political group they belong to. Right? So this idea of conditional probabilities, that's what we're doing. The other one I always give, but it doesn't work as well in the spring semesters. But let's imagine, right? This is just across any day in the year. What's the probability that if I'm walking into the building, I slip and fall? I haven't slipped and fallen yet, so pretty low, right? However, if it was a day like even today, but a day where it's really icy, it's really, really cold, it's kind of rain, snow mix, maybe like, was it Friday it was like that, right? The probability that I slip and fall is a lot higher, right? One of the things I'll never forget about when I was an undergrad is how many people I saw slip and fall off the bus in the winter, right? And so knowing the weather conditions greatly influence the probability of that event that I was thinking about, right? So that's the idea of conditional probabilities. But why does this equation hold, right? Why can I find that conditional probability as the intersection of those two events divided by what I'm conditioning on? So I'll try to give a visual. We'll get a couple of these. We'll return to this idea even on Wednesday, but I think this one will give a pretty good idea of why we can write it this way. Okay, well, there we go. So I've been drawing, up to this point, circles to represent the events. They don't have to be circles. I could draw them, it could be any shape. So I'm going to use rectangles here because I think it just helps fall in line with the numbers a little bit better. So let's say this entire area here, let's say is event A. And I tried to draw this in such a way that it looks like it's exactly half of the entire experimental outcome space, right? So let's say like 50% of the outcomes are in event A, okay? Let's say I then take this like little rectangle or square over here, and I'm going to call this event B, okay? So what is the probability of A intersected with B? Well, I tried to draw this to like exactly split it in half. So really this rectangle of B, which is entirely intersected with A, the way I do, this is a very extreme example, right? I'm trying to draw proportionally. Let's say it's 0.25, right? Like you can think about like you have two squares here and then like a large half up there. So if I ask you for just what the conditional probability of B is, right? Well, this is a unique scenario in which all of event B is within A, right? So if I'm thinking about event B, it's really the same as the event B intersected with A, because I'm drawing this as an extreme example. So we call this the unconditional probability of B. Oh, sorry. Try to get this all in one line here. Okay. What if I want the conditional, so we'll call this is the conditional probability of B. Because we're still looking for the probability of B, but we've now conditioned on something else. Okay? Well, if the area of B intersected with A is 0.25, and now that I know A has occurred, essentially what I'm saying is the entire experimental outcome space is no longer one because I'm telling you that A has occurred. So now the only outcome space left is 0.5, right? Or whatever the probability of A was. So here, we can think about the entire experimental outcome space left is no longer like out of one, it's only out of whatever the probability of A is. Right? And what's the probability that now that we know we're somewhere in A, what's the probability that we are in B? Well, out of this entire space of 0.5, 0.25 of it would be that I end up in event B, which is really wherever probability in A and B intersect. Okay? Now I drew this one as an extreme example so that all of B was within event A. Okay? So here it was kind of odd because the probability of B and the probability of the intersections were the same thing. Right? But what if that wasn't the case? Would this idea still hold? Well, let's go back here. Let's say now the probability of B, let's say I make it 0.3. But I just extend it up here, right? So now the intersection of A and B is still 0.25. And now when I condition on A, it goes back to the exact same thing, right? Because saying that I'm conditioning on A eliminates all of the possible outcomes that weren't in A, right? So that's why we don't use the probability of B here in the numerator, where we just use the probability of the intersection of A and B, right? Any questions on that? Well, it's kind of a lot. Just trying to give you an intuition behind why that equation holds, okay? Because it's essentially like once we condition on this other event, we're like limiting the space that we're looking at, okay? And I could actually come up with like a really crazy one. Like, let's say event B was actually all the way out here, right? Well, then it doesn't matter, right? Because once I condition on A, I'm still back to the same thing, right? It just matters where the intersection of those two events are. Okay? Any questions on that before I kind of keep moving here? We're okay with that? All right. Wait. We got that time. So there we go. So let's say, so that's what we just went through and found here, right? That the conditional probability of this event B is the intersection of these two divided by whatever I'm conditioning on. So here, when I'm conditioning on B, divide by what I'm conditioning on. Right? And it doesn't matter which way I write the intersection, right? So even if I wrote the intersection, the probability of B intersection with A here, remember what we said earlier, A and B is the same as B and A. It doesn't matter which way I say that. Okay? So if I work backwards from here, because I think the other way is a little less intuitive, but let's say I just rearrange these equations. So like we're going back a slide now and we're rearranging this. Multiply both sides by the probability of A. And the equation I would have is that the intersection of two events is the same as the conditional probability times whatever I'm conditioning on. And this is kind of nice because it doesn't matter which way I write this intersection, right? But if I write it this way, I could also find the intersection using a different conditional probability and then multiplying by whatever I condition on there. So there's really two ways of finding this intersection. Because it doesn't matter what order I write the intersection, that's the exact same thing. Right? The ordering didn't matter there. Okay? Any questions on this? Okay with that? All right. I don't know. I like the visual I did better than this one, so we can kind of ignore this. But the idea would be, you know, if I'm looking for the probability that I see A and B, what I'm really looking for is this place where they overlapped. So the likelihood that I'm kind of within, you know, I'm in there is, well, first I have to know that A has occurred. Well, if A is not very likely to occur, then it's very unlikely for me to see the intersection of A with anything else, right? And so that's why you're kind of thinking about is whatever I'm conditioning on, my space gets kind of limited down to just that area. And that's kind of what I showed over here. I liked what I did in the dot cam a little bit better than the slides. So we can kind of ignore this drawing. I think the other one makes a little more sense. So all we did was rearrange that equation there. And now we've got kind of, here's our summary. We've got that complement rule. We've got our addition rule for finding the union. And we can rearrange that a little bit, right? We said to find different components. And I can also have this multiplication rule where I can solve for the intersection, or I could rearrange it and I could solve for conditional probabilities. Okay. So once we have this multiplication rule, let's go back to our contingency table. Right? If I want a conditional probability, I can't directly get that from my contingency table. Like it's not one of the cells up here, right? But can I change the font here easily? No, there's some option. There we go. Let's make it real big. So if I want the probability of R1 given C2, I know that I can rewrite that as the probability of the intersection of the two, right? And then divide by whatever I'm conditioning on. That was the I'll go back in a second. That was the equation we had. So what I'm really looking for here is the Oh, I'm gonna have to write it in words. Well, can I do an upside down U? I know there's symbols somewhere up here. Forget it. We'll just do the intersection of the two. So intersection with C2, and then we divide by the probability of whatever we're conditioning on, which is C2 here, right? So where is the probability of R1 and C2? Probability of R1 and C2 is 0.2. The probability of C2, go down to the total, is 0.5. Right? So hopefully, oops. Oh, so with that, I was just kind of writing out as I was saying it because I have it on the slide here, right? So the intersection of R1 C2 divided by C2, so 0.2 divided by 0.5 would give us that 0.4, right? So even though we can't directly get it from that table, we can use, right? We can always find intersections and we can always find the probability of events themselves from this table. And that's a little bit of work. We can always find those conditional probabilities from that contingency table, right? It's just not quite as easy as finding just the intersection. So this is what we had last class. So we said, given that I know C2 has occurred, what's the probability R1 has occurred? So we could rewrite that as the intersection of those two things divided by the probability of C2, what we were conditioning on. Okay? It's very easy then to go get the intersection of, R1 and C2, which is 0.2. Probability of C2, we go down to the total, 0.5, and it's kind of where we ended up. Okay? So what we were thinking about there is, it was almost like, if I don't condition on anything and I just want to find just the probability of R1, the unconditional probability of R1, I just go over the total, right? If I imagine I have this huge experimental outcome space that has an area of 1, and of that area, 0.6 of it are outcomes that are in R1, okay, in that event. Once I've conditioned on C2, I'm no longer looking at the entire experimental outcome area. I'm only looking at half of it, right? And of that remaining half, how much of that remaining half is in R1? Well, if I look of that remaining half, 0.2 of that 0.5 area is in R1. And that's essentially 0.2 out of the 0.5 area is how we're getting that conditional probability. Right? We've limited the space we're looking at down to a smaller subset, but it could be once we've limited down to this smaller space, more of that space is made up of R1 than when we're looking at the entire experimental outcome space. Now, it could be less, could be more. Right? So let's think about instead, if I did this, look for the conditional probability where I said, given that C1 has occurred, what's the probability that I see R1? Right? So I'm still looking at a conditional probability of R1, but I'm conditioning on something else. Okay? Well, I can rewrite that as the intersection divided by whatever I'm conditioning on. I can get the intersection of R1 and C1 is 0.4. The probability of C1 is 0.5, and I can compute that conditional probability. But what this is really telling me is, well, look, if I'm not conditioning on anything, 60% of that space is in R1. However, if you tell me that C2 has occurred, I said that I'm limiting the space I'm looking at to just half of that area, so 0.5. And of that 0.5 area, 0.2 is in R1. But if I condition on C1, it still limits the entire experimental outcome space down to an area of 0.5. But of that remaining area of 0.5 that's in C1, 0.4 of it is in R1. So knowing that C1 has occurred, it's much more likely that R1 has also occurred, right? Than if I'm thinking about if I tell you C2 has occurred, it's not near as likely, right? Only half as likely, or probably is half as large. Okay? So this is kind of a review of how we find these conditional probabilities, kind of what they represent to us. And what we're really thinking about here is like having this additional information really allows me to update my probability of whatever event I'm interested in. So we're going to look at a definition with this in mind, which is if events are independent. Okay? So we said that two events are independent if this unconditional probability of A, right? We're not conditioning on anything. We're just kind of think about it as like the normal probability, right? normal probability of A, if that is equal to the conditional probability of A, right? We're still looking for the probability of A, but we're conditioning on this additional piece of information. If those two things end up being the same, well, that means the additional information was worthless, right? It didn't have any relationship to that event A. So we would say that A and B are independent, because knowing that B has occurred doesn't change the probability that A has occurred at all. Okay? And then kind of we could do the other way as well, right? And the probability of conditional probability of B is equal to the unconditional probability of B. We'd say that A and B are independent. If A is independent from B, B is independent from A in these examples that we're looking at. Okay? So if we go back and think about our multiplication rule, we said we could rearrange the equation a little bit so that I can always find the intersection of two events by taking the conditional probability of an event and multiplying by what I'm conditioning on. Right? However, if events are independent, what could I plug in here instead of the conditional probability of B? Well, if they're independent, that conditional probability should just be equal to the unconditional, just the probability of B here, which gives us this kind of simplified formula, right? So if we have two events that are independent, finding the intersection is a little bit easier in that we can just take the probability of each event and multiply it by each other. Okay? And I'll talk through this a little bit more in a second with some examples. But with this definition of independence in mind, and kind of as kind of a byproduct of two events being independent, is that this equation should also hold, right? That the intersection of two events is just the product of the probability of each event, right? Or each event multiplied by each other. The probability of each event multiplied by each other. So if we look at a contingency table, right? What's the probability of A from this table? It's just I can wait through awkward silence. If I want the probability of A, what's the probability of A here? Yeah, I go over to the total column, 0.6. Right? So this, the probability of A is 0.6. Let's find the conditional probability of A. If it is equal to 0.6, we would say these events are independent, right? Having this additional piece of information didn't influence the probability of A at all. So I rewrite that conditional probability using my multiplication rule, that it's the intersection of the two events divided by the probability of what I condition on. The intersection of those two is 0.15. The probability of B here is 0.25, right? We can put that in our calculator, we end up getting 0.6. Sure enough, that's the same as the probability of A. We'd say these events are independent. Okay? You can kind of think of, you can kind of think about being independent as, let's say I'm thinking about eye color, and I say the probability that someone has blue eyes is 0.1. Right? Now I give you some additional information. I say, okay, what's the probability someone has blue eyes given that they're, I don't know, over 6 feet tall? That, I don't know, what does that being over 6 feet tall have anything to do with having blue eyes, right? It's still probably 0.1, right? If I took all the people over 6 foot tall, my guess is the percent of people that have blue eyes in that population is the same as the population as a whole. That event B had nothing to do with A. It was independent from A. Right? So that's kind of the idea of what we're checking for there. We could have also checked it using, seeing if the conditional probability of B was equal to the unconditional probability of B. And if A is independent from B, B should be independent from A. So we'll go ahead and check that. The probability of B here is 0.25. Rewrite that conditional probability of B. It's the intersection of those two divided by what we're conditioning on. So the intersection is 0.15. Probability of A is 0.16. Sure enough, that conditional probability of B is the same as the unconditional probability of B. So it didn't matter which way we used to check that, we would have found they're independent either way. Okay? Any questions on this before we keep moving? Yeah.
Are there any situations where one variable would be independent and the other one is dependent on the other variable?
So when we're talking about independence, think about this as the relationship. We're not trying to identify like which direction the relationship is. Like, it's not like A is a function of B. We're not talking about that. That very well could be that A is a function of B and B is not a function of A or something like that. But here, when we're thinking about independence, it's whether or not the probabilities of these things occurring are independent. So it'll never be the case where if A is independent from B, B will be independent from A. And the next check, I think, will hopefully kind of show why, because there's no way we could check it in two directions. So remember, I said if two events are independent, this would have to hold, right? So if the intersection of two events is equal to the probability of those events multiplied by each other, that was a byproduct of them being independent. Well, here, there's no way, if I'm checking this, there's no way I could check it differently for the direction of the relationship. So here, if I look at the intersection of A and B, that's 0.15, and then take the probability of A, 0.6, times the probability of B times 0.25, which ends up being exactly the same. Right? So this check kind of maybe helps us remember that if A is independent from B, B is independent from A. Like these two things are just independent from each other. These events. Right? And this is where like I'm using kind of using variables to check for this, or the way I'm talking about it, it's like variables that we're thinking about that could be independent from each other. But really remember, we're thinking about experimental outcomes. So it's like the outcomes, the probability I see an outcome in A is independent from seeing the probability of seeing an outcome in B. Yeah. Yeah, so let's say we went through and computed this and it was 0.3. Well, that's not the same as the intersection, so we would say they're not independent, or I guess you could say dependent, right? If we want to think about it that way. Any other questions on this? These are good. Okay. So we really just went through three ways we could check for independence, right? We could check to see if this holds, or we could kind of use the more definitions of these and then kind of use our contingency table to check it. And I put up here, I won't ask you like a question on this or necessarily like on the exam or anything, but one thing that I want to mention here, and I'm not going to go deep into the thought process. I might give an example here where I could relate this to it, but if two events are independent from each other, what ends up being true is the complements are also independent. So notice here, if I take A complement, probably the A complement and probably the B complement, I get 0.3. That's actually the same as the intersection of the complements. So if two events are independent, their complements will be as well. So think about it this way. Use an example last class. I think I like it. So let's say event A is that I have blue eyes, and event B is that I'm a registered Democrat, right? Well, those two things, if we use these probabilities, they're independent from each other, right? The probability someone I choose at random has blue eyes is the same as the probability that someone has blue eyes if I know that they're a registered Democrat. There's no eye color kind of differentials across the political spectrum. So if those two are independent, their complement should be as well. So not having blue eyes, right, having an eye color that's not blue, should be independent from being a registered Republican, right? The complement, if we think about there's only, let's assume there's two political parties for the sake of this example, right? So those complements, not having blue eyes and being a registered Republican, would also be independent. And that's kind of the idea that if two events are independent, their complements will be as well. So technically, there's a fourth way we could check. Right? If we wanted to check the complements first, that would also work. All right. So let's use this idea of independence and see how it kind of gets applied to some real situations. So I put here, so think about this as the Kenny Rogers or the gambler's fallacy, right? So we'll start out with this scenario. Think about if I flip a coin, what's the probability it comes up heads? 50% or probability of 0.5. Right? If I keep flipping a coin enough, like let's say I flip it 10,000 times, I know that if I were to count the number of heads out of 10,000, it should be right around 50%, right? Maybe a little bit off, but if I could do an infinite number of coin flips, I'd see 50% come up heads. So because I know that in the long run, it kind of hits this 50% mark, what we see a lot of people is fall victim to a fallacy. So if we remember that each coin flip is independent, right? So I flip a coin, I see some, heads or tails. I then flip a coin again, I see either heads or tails. do you know, like at what point, right, am I going to start to maybe fall victim to this gambler's fallacy? So if I say I saw 9 heads come up in a row, right? I know it's a fair coin, but I see 9 heads come up in a row. What might I be, what would the probability of seeing a heads on that 10th coin flip be? 50%, right? But what you can fall victim to is if you know that in the long run, they have to even out. Some people say, well, if I see 9 in a row, I know it has to balance out, so like it has to be tails, right? Well, no, each one's independent from each other, right? So the probability is still 50%, right? Doesn't matter how many consecutive heads you see in a row, the probability you get heads on the next coin flip is always going to be 50%. So you can go through, and I use Excel, I simulated coin flips, and you can kind of look at, these are essentially conditional probabilities. Conditioned on seeing just 1 tails prior, what's the probability I see heads on this coin flip? 50%. If I look at all the scenarios in that simulation where I saw previously 2 consecutive tails, what's the probability the next coin flip was a head? 50%. What about the times where I saw 3 previous tails or 4 previous tails? What's the probability I see a head on the next flip? It's always 50%, right? Kind of floating really, really close to that 50% level. So it doesn't matter, right? If we condition on the outcomes of the previous events, it doesn't influence the probability of the current event at all because they're independent, right? Each one of these conditional probabilities, if the current coin flip is independent from the previous coin flips, all these conditional probabilities should be the same as the unconditional probability, just the probability of getting a heads, which is all 0.5, okay? So we see people fall victim to this, though, a lot where if they see a long streak of consecutive outcomes the same, they think that the other outcome, right, has to be more likely, or that the probability has changed, which is not true. And in fact, there's a good example. So if we go back, what was in 1913, if we have a roulette table, basically you can think about it as if I spin it, there's a 50% chance this little ball lands on red, and there's a 50% chance this little ball lands on black. I know there's a green space, but for the sake of this, think about it, it's just the same thing, right? So that's really close to 50%. So there's this one instance, they spin this wheel and it comes up black 26 times in a row. Okay? Example, I want to do a sheet and point this out. I think there's one, on the next Connect homework, I might have a question that we have to think about this. So, if I think about the probability that a coin flip comes up heads, it's 0.5. Or we could think about it as that example with the roulette table. I don't know, the probability it comes up black is 0.5. Well, what's the probability that it comes up black on the first 2 spins? Right? So the first spin of the roulette table it lands black, and the second spin it lands black. Well, if they're independent events, we said the intersection of those 2 things should just be the probability of A times the probability of B. So the probability it comes up black on the first spin and on the second should just be 0.5 times 0.5. Right? And what about the first 3 spins? 0.5 times 0.5 times 0.5. 4 spins, so on and so forth. What's the probability that they saw 26 come up black in a row, which is what ended up actually happening? Well, it's basically 0.5 times 0.5 26 times, or 0.5 to the 26th. So anytime we have these independent events like flipping coins, and well, how likely is it if I flip a coin 10 times that I get 10 heads in a row? Well, you basically just take that underlying probability, and if the events are independent, you can raise it to the power of however many times you're interested in seeing that outcome in a row. So coming up black 26 times in a row, move the decimal point 8 places to the left, so 0.00000001. What's the probability of seeing that occur? Or pretty much, it was very, very, very unlikely. Right? We're starting to talk about like lottery level chances here. So I kind of want to point that out. That definition of independence kind of helps us out with examples like that.